Hi everyone. Thus far we have looked at Ka, acidity constant. We were able to calculate pH of different solutions, and you've also memorized the 7 strong acids and the 8 strong bases. In this video I want to go over some general trends so we can more easily predict whether one acid is stronger than the other. We're going to be focusing on mainly binary acids and oxoacids. Now, let's start with the idea of Ka and how it relates to acid strength. We know that the larger the Ka, due to it having much more products and reactants, the larger the Ka, the more apt for that acid to dissociate. So we could call this tendency to ionize. Tendency to ionize. And as that goes up, the strength of the acid goes up. And a nice visual to have is, let's take the general abbreviation for acid, HA, plus water goes to H3O plus aqueous plus the A minus aqueous. Should we go over the 7 strong acids one more time? Because the 7 strong acids, you will assume, dissociate nearly 100% or 100% ionized. So around 100% ionized. You will have to be good at memorizing or recalling the 7 strong acids, not only in this topic but also in the next topic. And that is HCl, HBr, HI, the hydrogen halides, or the halide acids, and I'll break them up into 2 sets. This one you want to memorize: nitric acid, chloric acid, perchloric acid, and sulfuric acid. Sulfuric acid is the one that is diprotic. Okay, and then the 8 strong bases. Again, you're going to assume that it's 100% ionized, but I'm going to put a little disclaimer of what is soluble. 100% of it is ionized. For some of these metal hydroxides that are bases, they're not fully soluble. But the first set are definitely are LiOH, NaOH, KOH. I'm doing this from memory, so I'm going down the periodic table for group 1. Rubidium, RbOH, and cesium, I think. The group 2, you skip beryllium and magnesium, and now we have, good question, now we have calcium, OH2, strontium, OH2, and barium. Those are your 8 strong bases. Okay, the first set of acids I want to compare are the binary acids. That's the HCl, HBr, those acids. Let's see. We already know that HCl, HBr, and HI are the strong acids, so HF is the one left out. And These are the binary acids. And those are the only four we'll look at for the binary acids. The trend is HF. It's much less acidic than HCl, HBr, and HI. But within those strong acids, these strong acids, we can say that HI is the strongest. Strongest acid. And out of these four, obviously, and then this is considered always a weak acid. So why is that the case? Before I go over any rationale why trend is true, let me give you the actual measured bond enthalpies in kilojoules per mole. Bond enthalpies, those are the energies required to break a bond. And I'll give you HF first, 563. Okay. So as the acids get stronger, they're more able to ionize, their bonds are easier to break. You would expect this number to track lower as you get stronger and stronger in acidity. 432, 366, and 298 for hydroiodic acid, the weakest bond. There are a couple ways to rationalize why this is true. I look at stability. So let's take a look at HI, and we have HI plus water goes to hydronium plus this I minus. And I'm looking at the stability of I minus. Out of all the anions from this set of acids, I minus is the most stable anion out of these possible four. And it's most stable anion. Just so we see the list, more stable than the other four, Cl minus, Br minus, and F minus. It wasn't really emphasized in General Chemistry 1, but it will be here and also definitely in organic if you take organic chemistry. This is true because I is bigger. The bigger size allows for I like to say to distribute the charge, the negative charge. For charged molecules and for charged atoms, the better you can spread out the charge, the more stable the species is. That's actually a very important tenet in organic chemistry. Maybe you heard about this when you were doing resonance, and that charge on a polyatomic ion was shifting between several different oxygens. But for now, let's just keep it with these binary acids. And why is that? Why does the stability of this conjugate base reflect on the acid? Well, if this is a fairly stable conjugate base, then yeah, you would want to go to the more stable species, motivating this acid to lose its proton. Not only that, because this is fairly stable, then that means this bond is weaker. That's one explanation. The other explanation still has to deal with size, and we could say here, what can we say? We could say the large radii of iodine makes the bond weaker. Remember, remember in Gen Chem 1 where the longer the bond, the weaker the bond? That's why triple bonds, which are short, are stronger than double bonds, and double bonds, which are shorter than single bonds, are stronger than single bonds. So the longer the bond, um, the the weaker it is. And I'll leave it at that. Okay. Because we do have to move on to the oxoacids. This is letter C. Remember the oxoacids? There are two trends for oxoacids. Trend 1. An oxoacid is a acid of a polyatomic ion that obviously has oxygen. For instance, HClO4. Well, let's go with 3. 3 has a larger Ka, and we're going to change the halogen again. HBrO3 greater than HiO3. So now in this case, the one that has Cl is the stronger acid. All of these are pretty weak acids though, right? They're not part of the 7 strong acids. So what's happening here? Simply, if you look at the Lewis structure, and yeah, let me go ahead and fill in the lone pairs. Now, many of you know that some of these oxygens have a formal charge, but overall, this is a net neutral. Okay, let me put a brackets here actually. If we feel a little bit better, and yeah, this is net neutral, 0. As chlorine, okay, which is more electronegative, oops, I didn't write HCl3, this is HCl4. Let's get rid of this bond right here. My bad. This has lone pair now. Alright. It's still net neutral, but chlorine is more electronegative. Than Br and iodine. So it's pulling. And true, I know the oxygens are also electronegative, but there's a general pull towards this chlorine when we look at this bond. And what that does is it weakens this bond right here. So it weakens bond. The more electronegative the central atom is, the more weak this bond is between O and H. So this is the central atom, just remember that. We're looking at the central atom. It's a little bit tricky because it's a different trend than what we saw with the binary acids, right? Chlorine is more acidic than HF, but it's less acidic than HBr and HI. So take a look at those two. HCl is less acidic, but in this case, not HCl, but HClO3 is more acidic. That's because we're not looking at the charge of that atom. This was again based on the charge and the stability of the conjugate base. Okay. And the size also, which makes the radii or the bond longer. Well, we're not looking at this bond. We're looking at this bond. We're going to depend on the electronegativity. So that's trend 1, trend 2. Maybe this is the more important of the two, the number of oxygens. So now let's go ahead and put HCl4. The more oxygens, the stronger the acid. Let's keep it all chlorine. And the rationale for this case is, again, the more oxygens. So, okay, so now let's put HClO4. The more oxygens you have, the greater a pull still. So now you have pull here, pull here, pull here. Okay, and then chlorine is going to pull also. Okay, making this bond weaker, much weaker. Then if you had just one oxygen, making too many typos. HOCl O. How does this one look? You have two lone pairs on chlorine. Okay. So we could say that this is the stronger bond compared to this bond right here. This is a weaker bond. Okay. So that's topic C, oxoacids. I do want to just mention briefly the strength of the conjugates. Do I want to talk about that now? Why don't I save that for the next video? All right. We alluded to it here when we talked about the stability of the conjugate base. Okay. Well, in the next video, we're going to rationalize that if this I minus is very stable, it is not a very strong base, right? Because it's stable. There's very little motivation for it to grab a hydrogen and act like a base. So that's what we're going to talk about in the next video. The more stable a species is, the less reactive it is. And we could start now looking at the strengths of the acids and bases depending on its conjugate's stability. But for this one, just focus on the binary acids and the oxoacids.